Okay, welcome back, dear students, to the tutorial about spectroscopy. We have been discussing about rotational spectroscopy. In the last video, we had discussed about non-rigid rotator. Okay, and I think this would be the final video about rotational spectroscopy. In this video, we are going to discuss about spectra of polyatomic molecules. Okay, listen. Okay, first type is linear molecule, and I think you might have remembered that we have classified the molecules into four classes based on their moment of inertia. Okay, and first one is linear molecule. Second one is symmetric top molecule. Third one is spherical top molecule, and fourth one is asymmetric top. Okay, we want to discuss all of these type of molecules, and first is linear molecule, and we have studied that for linear molecule IB equal to IC not equal to IA, and okay, and this is a case of a linear molecule. IB equal to IC not equal to IA, and IA equal to 0. Okay, therefore the spectra will be similar as in the case of a diatomic molecule. Okay, because here IA equal to 0 and IB and IC are equal, so spectra will be same as that of a linear molecule. So the equation will be same as that of the diatomic molecule, that is epsilon j is equal to B into J into J plus 1 minus D J square into J plus 1 the whole square plus etc. centimeter inverse for a non-rigid rotor. Okay, and the spectrum will have same 2B separation modified by the distortion constant D. Okay, so all the discussion on diatomic molecule applies equally to the linear molecules as well. And 3 points have to be remembered here. And first one is the moment of inertia of polyatomic linear molecule is considerably greater than that of a diatomic molecule. Therefore, B will be much smaller. For a diatomic molecule, we know B is approximately 10 centimeter inverse, and for linear triatomic and polyatomic molecule, B will be 1 centimeter inverse and even smaller in the case of larger molecules. That is the first case we have to remember. That means the lines will be more closer. Separation will be very less. Okay. And second thing is, not all linear molecules are rotational active. For a linear molecule to be rotational active, it should have a permanent dipole moment. For example, OCS can rotational active, but OCO, that is carbon dioxide, rotational inactive because it have no permanent dipole moment. Molecules to be rotational active, it should have permanent dipole moment. If we substitute this oxygen by isotope, okay, it may not be rotational active. For example, molecules like OCO, if we substitute this oxygen as 18 and this oxygen 16, because isotopic substitution never change bond length and the charge of the electronic charges. Therefore, dipole moment cannot change. Okay, and the second point. And third point is in diatomic molecule case, we have only one moment of inertia. But in the case of, for example, if we consider OCS, not OCS, OCO, OCS, there will be two bond. So I am going to discuss that. In the case of diatomic molecule, we have only one bond length. Okay, one moment of inertia and one bond length, easy to measure. But in the case of a triatomic linear molecule, there will be two bond length, CO bond length and CS bond length. But we get only one moment of inertia. From that we cannot calculate, it is impossible to calculate the two bond length. But we can solve this case. For example, if we consider this molecule OCS, this is oxygen, suppose this is carbon and this is sulfur, and this is center of mass of the molecule. Therefore, this length is denoted as RO, and this length, that is from center of mass to sulfur, is denoted as RS, and from center of mass to carbon denoted as RC. And this is a bond length, we can denote it as RCO bond length, and this is bond length between carbon and sulfur, this is RCS. Okay, so RO, this RO, that is distance from center of mass to oxygen, is equal to RCO plus RC. This is RC, RCO plus RC. And RCS, this bond length, RCS, RS, that is distance from the center of mass to sulfur, this length, RS. So RS, we can write RCS minus RC, RCS minus RC. Okay, and we can that by balancing the moments, we can write MORO. MO is the mass of oxygen, RO is the distance from the oxygen to the center of mass, plus MCRC, that is this side, is equal to the other side, that is MSRS, by balancing the moments. And moment of inertia I is equal to MORO square plus MCRC square plus MSRS square. Okay, and substitute the values RO and RS in this equation, we get this equation, that is MO RO, we can write RCO plus RC, RCO plus RC plus MCRC is equal to MSRS, MS into RS, we can write RCS minus RC. Removing the bracket, we can write okay, that is MORCO plus MORC plus MCRC is already here, is equal to MS is here, into RCS minus MSRC. Taking this side, we get, and take this MORCO at that side, we get MORC here plus MCRC here, and this MSRC taking this side become plus MSRC is equal to MSRCS minus, this is taken that side, we get MORCO, and this we can write MO plus MC plus MS into RC is equal to MSRCS minus MORCO. And this MO plus MC plus MS, we can write the total mass of the molecule is equal to, we can write MRC is equal to MSRCS minus MORCO. Okay, then so we get this equation. That is MRC is equal to MSRCS minus MORCO. And our moment of inertia I is equal to MCRC square plus MORO square, RO square plus MS RS square. Substitute the values of RO and RS here. We get MC RC square plus MO. RO we can write RCO plus RC square plus MS. For RS we can write RCS minus RC square. And by expanding we get MC RC square plus, by expanding the bracket we get MO RCO square plus MO RC square plus 2 MO RCO RC plus, by considering here we get MS RCS square plus MS RC square minus 2 MS RCS RC. Okay. Taking these terms together, MCRC square, MORC square is here, and MSRCS RC square is here. Taking all these three together, we get MC plus MO plus MS, that is capital M into RC square. And from this we can 2RC here also 2RCs here. So 2RC into remaining is MO RCO minus here MS RCS plus this term, that is MO RCO square plus, and the remaining term is MORCO square and MSRC, this term MSRCS square. Okay, and that is equal to substitute value of RC here, RC value of RC is here, MSRCS minus MORCO divided by M. So we substituting this, we get M into, for RC we can write MS RCS minus MORCO divided by this square, here also M square divided by M. Okay, plus 2 into, for this RC again we can write MS RCS minus MORCO divided by M 2 RC, and again this term here, that is MORCO minus MSRCS plus again this term, that is MCRCO square plus MSRCS square. Okay, then this we have obtained, and now from this equation this one M is cancelled, and MSRCS minus MORCO square, here also MSRCS minus MORCO divided by M, these terms are here, so we can take in this outside, that is MSRCS minus MORCO divided by M, that is taken outside. One more, this is square here, therefore MSRCS minus MORCO, one more term is here, plus here the remaining term is, this time we are taken outside, then here plus 2 MORCO, 2 is here, minus 2 MSRCS, that is in the bracket, plus MORCO square plus MSRCS square. This we can write, that is MSRCS minus MORCO. Here MSRCS is here, 2 MSRCS. Okay, and MORCO, this term is plus 2 MORCO. So 1 MORCO minus MSRCS. Okay, divided by M is here, plus MORCO square plus MSRCS square. Okay, from this we can write, this is equal to, taking this as minus, we can write MORCO minus MSRCS. Okay, this take as minus. Therefore, this become plus, this become minus. Okay, so minus of square divided by M plus MORCO square plus MSRCS square. Okay, so this is our equation. Okay, this was we have obtained. So we can write like this: I is equal to, first we can write this term, that is MORCO square plus MSRCS square minus MORCO minus MSRCS divided by M. Okay, this is a equation for moment of inertia of OCS molecule. Okay, and if you substitute this, what was our aim? What was why are we deriving this equation? In this case, for a diatomic molecule like HCl, we have only one bond length. So one moment of inertia is enough to calculate the bond length. But in the case of OCS, you had two type of bond, but we get only one moment of inertia. From that, we cannot calculate two bond length. The one of the main application of rotation spectroscopy is the what? Main application of rotation spectroscopy is the calculation of bond length. So our aim, what I am doing is how to calculate these two bond length. So we get this equation and substitute, we take another molecule in which one of the atom is isotopically substituted. So we get O18CS. O18CS. Then the equation will be I dash MO dash RCO square plus MS dash RCS square minus MO dash RCO minus MS dash RCS square divided by M dash. From these two values, we can calculate the bond length RCO and RCS. This was our aim. This is there in the Banwell's textbook. Sometimes you may not follow what I am doing is, you please read the textbook and work out this problem, or work out this derivation. Okay. This is a case of a linear molecule. So for the linear molecule, the spectrum will be same as that of a diatomic molecule. But there is this problem, that is we have two bond length but only one moment of inertia. This can be calculated by isotopic substitution. Okay. And next is symmetric top molecules. For symmetric top molecules, for example, if you take CFCH3, another example for a proline symmetric top molecule. For symmetric top molecule, we know that IB equal to IC, not equal to IA, and IA not equal to 0. Okay. Here also two moment of inertia are equal and one is different, but that is not equal to 0. So the spectrum will be also somewhat complex, but not that too much complex, because two moment of inertia are equal here. One is different. So we need two. That is, here there are two quantum numbers. We need two quantum numbers describe degree of rotation. There are two types of rotation altogether. So we need two quantum numbers. So first, for two quantum numbers for two types of rotation. One rotation for the axial rotation about the CF axis. Other perpendicular rotation. That two rotations are equal. Therefore, we need two quantum numbers. And one, it is convenient to take the one quantum number as the total angular momentum quantum number, and that is total angular momentum quantum number is J. Okay, and another quantum number is K, and that is the quantum number for the rotation about the CF axis, rotation about the CF axis, and that is K. And the value of K is equal to minus J to plus J. That is, total value of K is equal to 2J plus 1. Total value is 2J plus 1. Okay. And by solving the Schrodinger equation, we get epsilon Jk, that is Ejk by Hc is equal to, very simple equation, B into J plus 1 plus A minus B K square centimeter inverse, where B h divided b, value of b is equal to h divided by 8 pi squared ib into c, ib or ic, anything we can use, and a is equal to h divided by 8 pi squared IAC. That is the value of B and A. Okay, and selection rule for this type of molecule, symmetric top molecule, delta J plus or minus 1 as before, and delta K equal to 0. So by taking this difference, that is E epsilon J plus 1 the state with the K value minus E epsilon Jk, we get this frequency of the absorption epsilon Jk is equal to B into J plus 1 into, that is first we are giving for J plus 1, so J plus 1 plus 1 J plus 2 plus A minus B K square, because K delta K equal to 0, minus B into J plus 1 plus A minus B K square, that is cancelled, we get 2B into J plus 1, same as that of a diatomic rotator. Okay, there is no spectrum for the, that is the spectrum of independent of K. Spectrum is, in this case we derived that independent of K. That is rotation about the CF axis or the principal axis does not bring about the spectrum. Rotation about this axis, that is CF axis, that is spinning of the molecule, does not bring about the spectrum, because it is evident, because by spinning like this, molecule spinning like this, there is no dipole moment creation perpendicular to the axis, no dipole moment, change in dipole moment in the perpendicular axis, so light cannot be absorbed. So in the case of rotation about the axis, there is no absorption. Okay, and we get 2B into J plus 1 value. So spectra of a symmetric top molecule is similar to the case of a diatomic molecule. And the other two cases, that is spherical top, no need to discuss, because in the case of spherical top molecule, we know that IA equal to IB equal to IC. Examples of spherical top molecules are CH4, tetrahedral molecule, and they have no permanent dipole moment. They do not show rotation spectra. So we don't want to discuss about this spherical top molecule. And for asymmetric top molecule, the last type, asymmetric top molecule, IA not equal to IB not equal to IC. The spectra will be very complex. I'm not going to discuss the details of the asymmetric top molecule. If you need, we may discuss the textbook. Okay, and this much about the rotational spectroscopy is over, and from the next class onwards we will discuss about the vibrational spectroscopy. I request you all, please read the textbook very well. All these are very well explained in Bandwell textbook. Please read the textbook very well, okay, and understand the basic theories about the rotational spectroscopy. Okay, thank you.